The term physical constant expresses the notion of a physical quantity subject to experimental measurement which is independent of the time or location of the experiment. The constancy, immutability, of any physical constant is thus subject to experimental verification. Paul Dirac in 1937 speculated that physical constants such as the gravitational constant or the fine structure constant might be subject to change over time in proportion of the age of the universe. Experiments conducted since then have put upper bounds on their time dependence. This concerns the fine structure constant, the gravitational constant and the proton-to-electron mass ratio specifically, for all of which there are ongoing efforts to improve tests on their time dependence. The immutability of these fundamental constants is an important cornerstone of the laws of physics as currently known. The postulate of the time independence of physical laws is tied to that of the conservation of energy, Newton's theorem, so that the discovery of any variation would imply the discovery of a previously unknown law of force. In a more philosophical context, the conclusion that these quantities are constant raises the question of why they have the specific value they do in what appears to be a fine-tuned universe, while their being variable would mean that their known values are merely an accident of the current time at which we happen to measure them. Dimensionality. Further information, system of measurement and natural units. It is problematic to discuss the proposed rate of change, or lack thereof, of a single-dimensional physical constant in isolation. The reason for this is that the choice of a system of units may arbitrarily select any physical constant as its basis, making the question of which constant is undergoing change an artifact of the choice of units. For example, in SI units, the speed of light has been given a defined value in 1983. Thus, it was meaningful to experimentally measure the speed of light in SI units prior to 1983, but it is not so now. Tests on the immutability of physical constants look at dimensionless quantities, i.e. ratios between quantities of like dimensions, in order to escape this problem. Changes in physical constants are not meaningful if they result in an observationally indistinguishable universe. For example, a change in the speed of light c would be meaningless if accompanied by a corresponding change in the elementary charge E so that the ratio E2:c, the fine structure constant, remain unchanged. Natural units are systems of units entirely based in fundamental constants. In such systems, it is meaningful to measure any specific quantity which is not used in the definition of units. For example, in stony units, the elementary charge is set to E=1 while the reduced Planck constant is subject to measurement, H137.03, and in Planck units, the reduced Planck constant is set to H=1, while the elementary charge is subject to measurement, E137.03 The 2019 redefinition of SI base units expresses all SI base units in terms of fundamental physical constants, effectively transforming the SI system into a system of natural units. Fine structure constant. For the fine structure constant, an upper bound on time variation of 10⁻17 per year has been published in 2008. In 1999, evidence for time variability of the fine structure constant based on observation of quasars was announced. Proton-to-electron mass ratio. An upper bound of the change in the proton-to-electron mass ratio has been placed at 10⁻7 over a period of 7 billion years, or 10⁻16 per year, in a 2012 study based on the observation of methanol in a distant galaxy. Gravitational constant. The gravitational constant g is difficult to measure with precision, and conflicting measurements in the 2000s have inspired the controversial suggestions of a periodic variation of its value in a 2015 paper. However, while its value isn't known to great precision, the possibility of observing Type Ia supernovae which happened in the universe's remote past, paired with the assumption that the physics involved in these events is universal, allows for an upper bound of less than 10⁻10 per year for the gravitational constant over the last 9 billion years. As a dimensional quantity, the value of the gravitational constant and its possible variation will depend on the choice of units. In Planck units, for example, its value is g=1 by definition. A meaningful test on the time variation of g is equivalent to the test on the time variation of the gravitational coupling constant, which is the square of the electron mass in Planck units and, if divided by the fine structure constant, is the ratio of gravitational attractive force to the electrostatic repulsive force between two electrons. Cosmological constant. Further information, cosmological constant, vacuum energy, and dark energy. The cosmological constant is a measure of the energy density of the vacuum. It was first measured, and found to have a positive value, in the 1990s. It is currently, as of 2015, estimated at 10⁻122 in Planck units. Possible variations of the cosmological constant over time or space are not amenable to observation, but it has been noted that, in Planck units, its measured value is suggestively close to the reciprocal of the age of the universe squared. Lambda T-2. Barrow and Shaw, 2011, proposed a modified theory in which lambda is a field evolving in such a way that its value remains lambda T-2 throughout the history of the universe.